Okay, let's unpack this. Imagine scientific discovery, but without the usual human limits, the bottlenecks.
Right.
What if an AI could just go off, explore the unknown, come up with ideas, test them, write it all down?
Yeah, I mean, that's the core idea here, isn't it? An AI scientist.
Exactly. So today, we're diving deep into this concept. We've got this source material outlining a framework that tries to fully automate scientific discovery, specifically looking at machine learning itself.
And it's the scope that's really ambitious. It's not just AI helping scientists.
No.
It's designed to be an independent researcher. From that first spark of an idea all the way to testing and, presenting the findings.
The whole shebang. It's trying to automate what we usually think of as, well, uniquely human science stuff.
End-to-end automation. It's quite something.
So this AI scientist, it basically works in three main stages, right?
Yeah, 3 key phases.
First, it comes up with the idea. That's idea generation.
The brainstorming part.
Then it actually, tests it out. Experimental iteration.
Runs the experiments, gets the data.
Exactly. And finally, it writes it all up. The paper write-up part.
And there's even that review step afterwards, a kind of quality check.
Right, like a simulated peer review to check the work.
Yeah.
Pretty thorough.
And the starting point is quite clever. It doesn't start from absolute scratch.
No. How does it begin?
It gets a basic working code template. Think of it like a simple functional model in whatever ML area it's focusing on.
Ah, okay. Like a foundation.
Exactly, a solid base. And from there, it's kind of free to explore any direction it thinks of.
And how it comes up with those directions, it's not just random, is it? It's based on, like, evolution.
Sort of, yeah. Inspired by evolutionary computation, it brainstorms lots of different research paths, builds up this whole archive of ideas over time.
Yeah.
And each idea isn't just a vague thought. It's got a description, a plan for experiments,
Wow.
and even the AI's own rating for how interesting, new, and feasible it seems. It uses layers of reasoning to refine them.
And it checks its work against what's already out there.
That's the really smart part. It connects to Semantic Scholar, searches the web, to filter out ideas that are too similar to existing stuff, so it's not just, rediscovering things.
That's crucial for actual autonomous research, isn't it? Context.
Absolutely. Knowing the landscape.
Okay, so it has an idea, it likes, it's checked, it's novel.
Then what?
Experiments.
Then it moves to the experimental iteration phase. It uses this tool, AIDER, have you heard of it?
Vaguely, yeah.
Yeah.
For coding assistance.
Exactly. It helps plan the experiments and then actually runs the code. And get this, it's pretty resilient.
How so?
If an experiment hits a snag like a bug, or it runs too long, AIDER actually tries to debug it. Fix the code, run it again.
Seriously, how many tries does it get?
Up to 5 attempts, I think. Tries to correct errors 4 times after the initial run, and after every run, it writes down notes, like a lab journal.
Wow. Okay, so it's iterating, debugging, documenting automatically.
That whole cycle, that's the core of the scientific method, right? Experiment, observe, adjust, and this automates it, potentially speeding things up massively.
Okay, so experiments run, notes taken, then it needs to share the findings. The paper.
Yep, the paper write-up phase, the AI just writes a full scientific paper.
Including the formatting, like latex and everything.
Yeah, takes care of the latex formatting too, which, for anyone who hasn't wrestled with it, that's how scientists make sure complex stuff like equations and citations look right.
That's impressive on its own. But why a paper? Why not just, I don't know, release the code or data?
Well, the researchers make a good case for it. A paper gives us humans a structured way to actually understand what the AI found. It's interpretable.
Okay, that makes sense.
And it fits into how science already works, right?
Yeah.
You can evaluate it using things like conference reviews. Plus, the paper format is just super flexible, used across so many different fields.
Right, it's the standard currency of scientific communication. And to check these papers, they built their own reviewer.
An automated one, yeah. Another LLM, basically trained and validated to score the papers almost as well as human reviewers can.
So they can actually scale up the evaluation process.
Exactly. It gives them a consistent way to judge the quality of what the AI scientist is producing. And that validation is key, knowing the reviewer itself is reliable.
Now, here's a number that really caught my eye. The cost. Apparently, it costs something like, what, $10 to $15 to generate one of these papers?
Around that, yeah. Less than $15. It's remarkable.
It really is. When you think about typical research budgets.
It hints at a future where maybe research isn't quite so gated by, huge grants and resources. Could really democratize things.
Open up scientific exploration much more widely.
That low cost highlights the efficiency gains. You could potentially explore so many more ideas than we can now.
Okay, so they tested this AI scientist in a few different ML areas. Where should we start? Diffusion models.
Sounds good. That's the tech behind a lot of those AI image generators people are playing with. One paper it wrote was called Adaptive Dual Scale Denoising.
Right. What was the big idea there?
The core insight was about improving these models by processing the image data at two levels simultaneously.
Two levels.
Yeah, like a global level for the overall structure and a local level for the fine details. And the really neat part was it came up with a learnable way to kind of adjust the balance between those two levels as the image is being generated.
Oh, interesting. So it dynamically figures out how much big picture versus detail focus is needed at each step.
Precisely. The idea being that combining both effectively is key to good diffusion results, and the AI found a way to manage that mix.
And it didn't just think of it, it actually coded it up.
Coded it, yeah.
Yeah.
Made some specific design choices, like using a particular activation function, leaky rail U, I think it was. And it didn't just show the final images.
What else?
It automatically generated new kinds of plots, showing how that weighting between global and local changed during generation.
That's genuinely novel visualization.
Yeah.
Did it work? Were the results good?
The results looked promising, yeah. Improvements in image quality, both visually and based on quantitative metrics like KL divergence.
Okay.
And the paper even suggested logical next steps for research, like trying it on more complex data.
Were there any, like, funny quirks, AI weirdness?
A couple of amusing things, yeah. It tended to frame everything super positively. Even if a metric went down, it might call it an improvement somehow.
Huh. Optimistic AI.
And sometimes bits of the internal logs, like references to run 2, would sneak into the final paper text.
Little artifacts.
Yeah. And it included results from literally every experiment it ran, which isn't typical. Also, the bibliography was pretty small, only 9 references, despite having access to Semantic Scholar.
Interesting trade-offs. Was there another diffusion example?
There was Dual Diff, which also explored combining different networks, but took a different approach with, like, a diversity loss to make the network specialize. Shows it can explore variations on a theme.
Okay, let's switch gears. Language modeling. That's a crowded field. Harder to find big wins there, right?
Definitely tougher. And they saw some common failure modes, like ideas that accidentally cheated by looking at future words, giving unrealistically good scores.
The classic look-ahead problem. Any interesting papers that didn't cheat?
One called Style Fusion sounded cool. It proposed adding a kind of style adapter for each word to modulate the transformer state. It got strong results.
But there's always a but.
But the researchers suspected the gains might just be from adding more parameters, more knobs to turn often helps, even if the idea isn't revolutionary. And some implementation details were apparently missing.
Okay, another one.
Another was adaptive learning rates in transformers via Q-learning.
Q-learning, like reinforcement learning, to set the learning rate.
Yeah. Using RL to adjust how fast the model learns based on how well it's doing. Super creative idea.
Did it work?
It actually got decent results, but the researchers themselves were a bit skeptical, questioning if basic Q-learning is really the best fit for that complex environment.
Right. Sometimes creative doesn't mean optimal.
Exactly. And they also mentioned some technical hiccups. GPT-4o apparently struggled with the latex formatting for its paper.
Even the advanced models aren't perfect. Which models works best overall?
Claude Sonnet 3.5 seemed to produce the highest quality papers generally. GPT-4o was next, despite the latex issue.
What about open models?
They tried things like DeepSeek Coder and Llama 3.1 405B. Cheaper, obviously, but had more issues with, like, calling the tools correctly or overall quality. Llama 3.1 was weakest, apparently.
So there's still a gap between the top proprietary models and the open ones for this kind of complex task.
Seems that way for now, yeah. Though the researchers want to use open models more going forward, especially for self-improvement stuff.
Okay, third area, grokking analysis. Remind us what grokking is again?
Right. Grokking is that weird, fascinating thing where a model seems to just memorize the training data for ages.
Yeah.
And then suddenly, much later, it just clicks and starts generalizing really well to new data it hasn't seen before.
That sudden jump in understanding.
Exactly. So the AI scientists generated papers trying to figure out why and when that happened.
So less about performance, more about understanding the learning process itself.
Precisely. One paper looked at how initializing the model's weights differently affected grokking. Found some initializations made it happen faster.
Interesting. What else?
Another one played with learning rates again, but but this time layer by layer, showed that speeding up learning in the higher layers helped grokking happen faster and more reliably.
That connects back to the language model paper, using learning rates creatively.
It does, yeah. Seeing similar themes emerge, then there was one trying to link grokking to minimum description length, MDL.
MDL, like finding the simplest explanation.
Kind of, yeah.
Huh.
The idea that generalization is about finding a compressed representation. But the researchers found problems with how the AI actually measured MDL.
Uh-oh.
And apparently, it hallucinated a plot in the paper, just made it up.
Whoa, okay, that's a reliability issue.
Definitely. And that paper, plus another one on using data augmentation to speed up grokking, were both missing the related works section.
So consistency issues, some potential factual errors, but still exploring interesting fundamental questions.
Exactly. It shows the potential for this AI to do more exploratory, why does this happen type research, not just make the number go up, but also flags those weaknesses, like missing standard paper sections or, making up plots.
It really is impressive how it tries to put these different pieces together, though. The researchers really stress that it's doing more than just, say, optimizing one part of a pipeline or analyzing data.
Right. It's tackling the whole research process.
Yeah.
Ideation, experimentation, writing, review, that full loop.
That's the key difference from a lot of prior AI for science work, isn't it? The comprehensiveness.
That seems to be the main claim, yeah. Full automation of the cycle, using the paper as the output.
Which brings us back to the why papers question. We touched on it, but it's worth reinforcing.
For sure. Interpretability for humans is huge. Integration with the existing scientific evaluation system, like peer review, and just the paper as a flexible, established way to share complex results.
Makes sense. And resource-wise, this wasn't done on some giant supercomputer cluster.
Surprisingly light, actually. Mostly used a single node with 8 H100 GPUs for about a week for hundreds of experiments. The main cost driver wasn't the computation for the experiments.
That was the LLM calls.
Exactly. Using the APIs for the coding and the writing, that's where the bulk of that $15 per paper cost comes from.
Gotcha. And we talked about the different models they use, the open versus closed trade-off.
Yeah, Sonnet 3.5 on top for quality. But open models like DeepSeek and Llama offering advantages in cost, transparency, and customizability, even if performance isn't quite there yet. They see potential in open models for future work.
So looking ahead, what's next for the AI scientist? Where could this go?
Lots of directions. They mention adding vision capabilities so it can understand plots and figures better, maybe even generate them more reliably.
That seems crucial. What else?
Integrating human feedback more formally. Letting it use the internet to find new data sets or models, with safety checks, of course.
Okay, expanding its access to information.
And even having the AI research its own code, try to improve itself.
Whoa, self-improving AI researchers. That's meta.
Right. And then the big one, applying it to other scientific fields, biology, chemistry.
Hooking it up to robotic labs, maybe?
Potentially, yeah. Cloud labs are a thing. But that obviously raises the stakes massively in terms of reliability. You can't have an AI hallucinating results when it's mixing real chemicals.
Absolutely not. So better automated verification becomes even more critical, tackling that hallucination problem head on.
Paramount, especially if it moves beyond simulation into the physical world.
So wrapping things up, what are the big takeaways here for you, for the listener? This AI scientist feels like a pretty major step, doesn't it?
It really does. A significant step towards AI playing a much more active role in research. It definitely makes you think about how the job of a human scientist might change.
Yeah, maybe less about running every single experiment, more about asking the big questions, guiding the AI, interpreting the results.
Could be. Empowering humans to tackle bigger, more ambitious ideas, perhaps. But the really deep question, the provocative thought maybe,
Don't worry.
can an AI like this, however sophisticated, really make those huge paradigm-shifting leaps, the kind of breakthrough that comes from, I don't know, true intuition or creativity?
Or will it mostly accelerate discovery within existing paradigms? Can it have a truly original aha moment that reframes a whole field?
That's the multi-billion-dollar question, isn't it? We don't know yet. This system is amazing at exploring, iterating, optimizing within a framework, but can it invent a whole new framework?
A fascinating question to ponder. This dive really gives us a glimpse into a potential future for science. It makes you wonder how this could accelerate progress everywhere and how it might change how you approach learning new things yourself.
It definitely forces us to think about creativity, discovery, and the partnership between human intelligence and artificial intelligence. This AI scientist is a powerful early example of what that partnership might look like.